This is the video for section 7.5 on strategy for integration. And the point of this section is to talk about what happens, in an exam situation like we just had, where you're going to be asked to compute integrals or antiderivatives, and you're not going to be told what technique to use because you don't know, right? It's not coming from a specific section. And so the book has a fairly specific strategy that's outlined in points and subpoints and such, and I'll let you read that. Let me give you the brief version of that. And so it comes in a number of steps. The first thing that you should do is try and simplify the integral. If you can. So if you have something that's in terms of tangents and cotangents and cosecants and such, unless you see something obvious to do, you should turn everything into sines and cosines and see if you can cancel to get something nice and simple. Okay? The second thing to do, and this is your general go-to strategy, is to look for a U substitution. Right. And we've talked extensively during the semester about techniques for recognizing when there's a substitution that's going to help you with your integral, particularly if you have something like stuff to a power or sine of stuff or e to the stuff. Whenever you've got one expression acting on a more complicated expression, generally that stuff, e to the stuff, that stuff is going to be a good choice for a substitution. And then we have a series of standard techniques that break down according to the sections that we looked at. For instance, if you have trig functions, then you want to employ the techniques from section 7.2. Right? So when you have products of secants and tangents and things like this, that you're probably going to want to use a substitution of tangent or secant depending on the exponents that are occurring in the powers of tangents and secants that you have, and same with sines and cosines and such. You might have a rational function. So that's a quotient of one polynomial over another polynomial, and in that case you're probably going to use the techniques from section 7.4 on partial fractions. Now this, of course, each of these falls into the category of you should try and simplify first to see if there's a way that you can simplify to avoid having to do one of the more extensive techniques. So in part A, that trig functions generally come as products. Other products that might come up is a situation where you would want to use integration by parts, right? So section 7.1. And then part D is if you have some sort of a radical expression. And the two primary cases that we'll see, case one is if you have a square root of a quadratic function, and this is a situation where you can do completing the square in order to apply an appropriate trig substitution. Right, and so those are the techniques from section 7.3. Or if you have something simpler, like the square root of ax plus b, then you would try a rationalizing substitution as was discussed in section 7.4. So that's where you use a substitution of u equals ax plus b in order to hopefully transform the integral into one that is a rational function that you can use partial fractions to understand. Now, Two things about this strategy. The first is you don't have to do these steps in order. Okay? If you see that this is a rational function that can't be simplified and you want to do partial fractions, then you should just go for it. You don't need to check and see automatically if you're going to use trig functions to do that. Okay? So this is a fairly dynamic strategy. It's listed this way so that you can see it in terms of bullet points, but if you can see exactly what technique you should use right away, then you should use that technique right away and not spend time going through the steps of the strategy. The second thing is that this strategy doesn't always work, right? It might not be one of the standard techniques. There might not be an obvious substitution or an obvious simplification. And when this is the case, you have to go to step 4, which is really the last step, which is to try again. And this is a terrible catch-all for what's left, right? So, for instance, if there's not an obvious way to use integration by parts, we've seen that there are situations of functions that aren't products where integration by parts can help, right? We've seen situations where it's not clear that you should try to use a substitution, but there's a clever substitution that you can use, for instance, before you use integration by parts. Okay, so this is possibly the most creative part of the course, where you have to problem solve and figure out what the heck technique is going to help you to turn your integral into something that's in a standard form that you know how to do. And this is always the goal with these strategies, is to take a complicated integral that you don't know how to deal with, problem solve, investigate, trial and error, to get down to something that you can actually integrate. I've done integration by parts 5 times, and now I'm down to the integral of cosine, which I know how to do immediately. Okay? So what we're going to do for the rest of this video is to just go through some examples of applying the strategy. I'm not going to work through these examples in complete detail. I'm going to do a little bit of analysis of the integral. I'm going to give us an idea of where we should go in order to actually evaluate the integral, and then I'm going to leave the actual evaluation of the integral to you. Okay? So we'll do that over here, say on the right hand side, so that we can keep the strategy in mind while we do the first few of these. So for example, if you were going to look at the antiderivative of 3x plus 1 to the square root of 2. That's a square root of 2 up in the exponent there. Dx. Okay. So hopefully you look at that and you see, well, square root of 2 up in the exponent, I can't multiply that out, so there's not really a nice way to simplify that. But I do see that I have stuff to the square root of 2. And that stuff is something that when I take the derivative, du equals 3 dx, and that constant is always something that I can deal with in doing a nice u substitution. And then I'll essentially have u to the square root of 2, which I can take the antiderivative of just by using the power rule. Next example, the antiderivative of x over 2x plus 1 cubed dx. So again, here's a situation where if the numerator and denominator were switched, so you had the 2x plus 1 cubed on the top and the x on the bottom, then it would help to simplify. By just multiplying out the 2x plus 1 cubed, you can divide through by the x and integrate that term by term. A substitution is not going to help here, because if you have stuff cubed down in the bottom, and so your 2x plus 1 cubed, you might try a substitution, but when you try du, which is just 2 dx, you're not going to get something that simplifies particularly nicely. Actually, now that I look at that one, you could do a substitution. Let's try that actually. So u equals 2x plus 1, and then we would have du equals 2 dx, And x can be written as, subtract the 1, divide by 2, 1/2 u minus 1. And so we could then simplify this antiderivative. So I'm off by a 2 for my dx, so I need a 1/2 on the outside. So we get 1/2 antiderivative of my x expression, 1/2 u minus 1. There's my 2 dx, which is du, and then I have u cubed on the bottom. And so that's one that I can then simplify and integrate term by term. Okay. Now, when I initially picked this example, I looked at that and I saw, well, substitution's not going to help because I have more than just 2 dx up in the numerator. And the other technique that you could use in order to evaluate this would be partial fractions. Yes, partial fractions. Because then you would write x over 2x plus 1 cubed as a over 2x plus 1, which you know how to integrate, plus b over 2x plus 1 squared, which you know how to integrate, plus c over 2x plus 1 cubed, which you know how to integrate. Okay? So either of these techniques would be perfectly correct for evaluating this integral. I think that substitution is probably going to make the integral go faster, which is, if you have a choice, the strategy that you want to use is, of course, the fastest one, as long as you maintain your efficiency in getting a correct answer. Okay. Next example is the antiderivative of t times sine t times cosine t dt. Excuse me. Now, if you're a normal person, you look at that and you say, well, that can't really be simplified. There's nothing to multiply out, no terms to be collected or anything like that. There's not an obvious substitution here, because if you tried to substitute u equals tangent at t, or u equals cosine t, then you'd have your du, but then you have to deal with this leftover t here, which is not an obvious way to do that without invoking inverse trig functions, which I would avoid. Okay. So substitution doesn't look very helpful. It's got trig functions in it, but it's also got this messy t in it. So your standard technique from 7.2 is probably not going to help. It's not a rational function. So you look at that and you say, well, maybe I should treat it like a product and do integration by parts. And once you've set on that as an idea, the hard part is to figure out what's my u and what's my dv. In order to go forward with integration by parts. And there are two ways to think about this, right? In general, you want to choose a u that when you take the derivative of it, it's going to go away. The problem is that you then have to make the rest of this equal to dv. And what are you going to do with that? Well, that's one that you can integrate pretty straightforward by using a substitution. So one technique for dealing with that would be, so for the antiderivative of sine t cosine t dt, you could either use a substitution of course we're using a different letter now, I'll call it W equals sine t. Or if you're remembering all of your trig identities, you can remember the trig identity that says that sine 2t is 2 sine t cosine t. And you can simplify that antiderivative rather easily. Okay? So this is one that you would want to use parts and be clever or just steadfast about how you evaluate that trig integral in order to figure out what your v is. So, next example, let's split the whiteboard in half here as best we can. Example of something like the antiderivative of x squared over 1 minus x squared inside a square root dx. So, how are we going to approach that one? There's not a nice way to simplify it. Don't be tricked into trying to split that square root in the denominator across the difference. That doesn't work. A substitution, that might work, although it's not an obvious way that that would work, because if you used u equals 1 minus x squared, you would then have du equals minus 2x, which you would have to deal with the x squared in the numerator. And then maybe if you're jumping ahead, you think to yourself, okay, I've got that square root of 1 minus x squared in the bottom. I need to, that's, come on, we already played with those. Those are the trig substitutions. And for this particular one, we would use the substitution of x equals sine theta. Right, so this is one that fits into one of the standard forms, so we don't have to jump through, is it trig functions, is it rational functions, is it a product? No, no, no. It's got that special radical form. We don't even have to go through and complete the square on that one. Right, now we get to some fun ones. So, antiderivative of sine of square root of a t, where a is some number. Now, with this one, of course we're integrating with respect to t. This one, okay, there's no way to simplify that. There's a substitution that you could do of u equals at, but that's not going to help you to get rid of the main problem in this antiderivative, which is that you have sine of square root of something. Okay. It's trig functions but with a mess inside, so you can't use the standard techniques from 7.2, and if you look through, it doesn't fit with any of the other standard techniques. So this puts me down at step 4, which is try again, and the way I see it, there are a couple of things that you can try to do. U equals at will help to make things look a little bit simpler, but it doesn't make the integral that much easier. And so you have sort of two options. You could either try one of those parts, right, where you have u equals sine of square root of at and dv equals dt. I'm not absolutely convinced that that will give you anything helpful, but I didn't play with that one, so maybe we can try that one on our own and somebody can let me know if it works. The thing that I see that you can try is a substitution, and the substitution I would use is, I'm going to call it x equals the square root of at. And let me give you an indication of why this works. So in this situation we have dx equals 1/2 1/2 square root of at times a times dt by using the chain rule. And so, right, this isn't an obvious thing to do because up here in the integral there's my u, but I don't have, sorry, there's my x, but I don't have the dx present inside my integral. But what I can do is I can solve for dt. So dt in this case is going to be, I'm just going to move all that stuff over, so it's going to be 2 square root of at all over 2 times dt, and that, apparently 2 equals a here, so let's fix that denominator, and let's fix that t while we're at it. This expression up in the numerator is exactly my x. Goodness, I've got a bunch of errors in here. That should, of course, be not dt, but dx. There we go. So, what's the upshot? Is that I have dt equals 2 over a times x dx. And when I put that into my integral, we end up with the antiderivative of sine x, because there in red is my square root of at, which is x, and then I multiply by my dt, which is 2 over a x dx, and I'll rewrite that as 2 over a, constants come out, antiderivative of x sine x dx. And this is one now that I can use integration by parts in order to evaluate. Right? Straight up. 2 more examples for us to look at inside this section. The next example is the antiderivative of tan inverse x over x squared dx. Ooh, right, so you look at this one and you can't simplify it. There's not an obvious substitution. Derivative of tan inverse is 1 over 1 plus x squared, but that just x squared in the bottom, not helpful. It's not standard trig functions. It's not a rational function since the numerator is not a polynomial. There's not a radical in there. So you're really kind of left with playing around with integration by parts. So I see 2 pieces in this integral. There's a tan inverse of x, and there's an x to the minus 2 dx. And one of those is easy to take integrals and derivatives of, and one of those is only easy to take derivatives of. So I would choose this to be my u, and this to be my dv, right? And see what happens when you get down to using integration by parts on that. And I'll tell you what's going to happen. You're going to end up with something of the form uv, which you don't have to do anything with, plus the antiderivative of 1 over x times 1 plus x squared dx, which you can now use partial fractions in order to evaluate the leftover piece of the integral there. Okay. Notice that I went through the strategy really quickly because I recognized very quickly that none of the techniques as they're laid out in the standard form are going to help me. Okay? And a good lesson to keep in mind is, when in doubt, substitution or integration by parts is probably going to be the technique that gets you where you want to be. Last example for this section is for us to look at the antiderivative of 1 over x squared times the square root of 4x plus 1 dx. And for this, hopefully you scroll through the strategy and you see, okay, I've got a radical expression down there in the bottom. That's a 4x plus 1 inside the radical. Let me write that out a little bit more clearly. And so you want to try one of those rationalizing substitutions of u equals 4x plus 1. And when you do that, you have du equals 4 dx, and we need to solve this expression for x. So x equals 1/4 u minus 1. So x squared equals 1/16 u minus 1 squared. And so here in my integral, I need a 4 to go with my dx, so I multiply by 1/4 on the outside, and we have 1/4 antiderivative of my 4 dx is now my du. On the bottom we have 1/16 u minus 1 squared times the square root of u. Apparently I've forgotten how to do rationalizing substitutions. This is of course not the way. So rationalizing substitution is correct, but this is not the u that you want to use. So let's try that again on the next page and then we'll be done. So back to the drawing board. We are looking at the example of 1 over x squared square root of 4x plus 1 dx, and the rationalizing substitution we want to use is not u equals 4x plus 1, but u equals the square root of 4x plus 1. And here we get that du works out to be 1 over 2 square root of 4x plus 1 times 4 dx. But more importantly is for us to go and actually solve for u and solve for x. So we have u squared equals 4x plus 1, and this is a much more convenient way to figure out what du is, because if I take the derivative of both sides, we have 2u du equals 4 dx. And so the point of this is that I have now an expression for dx in terms of u, so dx is 1/2 u du. And I can also solve what's my x squared going to be. So we have x equals 1/4 u squared minus 1, so x squared is 1/16 u squared minus 1 squared. And when you put all of that into the integral that we have over here, right? So I have the antiderivative of 1 over my x squared, which is 1/16 u squared minus 1 squared. I have my 4x plus 1 inside a square root. That's exactly my u. And let's highlight those in color. So there's x squared, which goes here. Here's square root of 4x plus 1, which goes here. and then I have my dx, which I'll put upstairs, and that's 1/2 u du. Notice that cleverly simplifies nicely to give us something that we can integrate straight away. Whew. So keep your head straight. If you find that you make a mistake, the part 5 of the strategy is don't lose your head if what you try doesn't work. Don't be afraid to go back to the drawing board and try something else, just like we did in that last example. Alright? So that's the end of the video for section 7.5.